Hello and welcome back to Dr. Logic Awkwardly Does Logic in her office. In this video, I want to talk about the notion of a good argument in propositional logic. Now, first of all, remember our definition of argument way back when. An argument just is a set of sentences that we call the premises and another sentence that we call the conclusion. Propositional logic has much more freedom than the syllogistic did. You remember syllogistic arguments could only have two premises, and they had to be the right type of form, they had to have the right number of terms and everything. Propositional logic is much more free and flexible. We could have no premises, we could have two premises, we could have 15 premises. It's unbounded. There isn't any limit. But the basic notion of argument is the same, and in fact, when we talk about what makes an argument a good argument, it's going to be exactly the same notion as in the syllogistic as well. Just instead of talking about interpretations, we'll be talking about truth value assignments. So the notion of good arguments in the context of propositional logic just is the notion of a valid argument. And this is one that is where every truth value assignment that makes the premises true also makes the conclusion true. Now, another thing that is interesting is that if you have a valid argument, you can always turn it into a single sentence, assuming that you have a finite number of premises. Take the conjunction of all of the premises and make this the antecedent of a conditional that has the conclusion as the consequent. If you have an argument and your argument is valid, then that corresponding conditional will always be a tautology. Pretty nifty thing. Once I teach you how to test for tautologies, the method in the short, efficient method, rather than writing out the full table, that same method you'll be able to use for testing whether an argument is valid or not. But I'd actually like to kind of just take a look at a particular argument and kind of walk you through how you can go about determining that something is valid. So let me bring up my whiteboard. The argument that I've put up here might look a little bit strange, but you might also remember it from when we talked about some of the Stoic arguments. So this says, if the first and the second, then the third, not the third, the first, therefore not the second. So the first thing that we've got here is we've got premise one, premise two, premise three, and our conclusion. Now, this is an English language argument. Well, it's kind of in this weird hybrid, the first, the second sort of language. But we can convert this very easily into a propositional logic one. Each one of these first, seconds, and thirds corresponds to its own atom. So here we have P, here we have P, let the second be Q, Q, the third be R, and then it's just a matter of identifying the logical connectives and forming the correct sentences. So what we can do is, first let's look for everything that looks like a logical connective. So every instance of and, every instance of or, every instance of if then, every instance of not. So these are the logical connectives that we have. So up here we have the first and the second. So that is a conjunction. Then looking at the kind of more wide scoping connective, we have the if then. So if the first and the second, if P and Q, then R. Premise 2 says not R. Premise 3 doesn't have any logical connectives, it just says P, and the conclusion is not Q. So what we can do is we can take this all in, let me see if I can do it in the middle of the screen here. So what this says is that if P and Q, then R, and not R, and P, then we have not Q. This is a tautology, and I will prove this to you. So I'll give you the full truth table because we haven't really done that many of these, and it's still useful to have examples, even if eventually I'm going to teach you the shorter method and you'll probably never draw a full truth table ever again. But we've got 3 atoms, so this means 8 lines in our table. the p's, half are true, half are false. And then we make half of the true p's true q's and half of them false q's. And same for the false p's. And then R is just alternating trues and false all the way down. So what we need to show, oops, this one needs to be true and this one needs to be false. What we need to show is that the column underneath the main connective is always true. Let's start off by looking at the smallest components. So over here, I'm just going to draw, oops, I wanted a different color. There we go. I'm just going to draw a column here for this not Q, just so that it's easier for us to kind of keep track what we're doing. We have true, true for Q, false, false, true, true, false, false. So not Q is going to be exactly the opposite of that. False, false, true, true, false, false, true, true. Now, what we are trying to do is we're trying to determine the truth values that go underneath the implication connective, because that's the main connective. Not Q is our antecedent, our consequent, and we know that every single conditional with a true consequent is itself true. So that means that we don't even need to look at the antecedent for 4 of these rows. We already know that those are true. The case where the other ones are all false are the important ones. So let's go back and look over here. Let's focus on this P and Q right here, because that is kind of the smallest, simplest formula that we have. So P and Q is true when both P and Q are true. So that is the case in the first 2 lines. But then if you just look down all of the other lines, in every other line, every other row, at least one of them is false. So the conjunction is going to be false all the rest of the way down. And then let me just count to make sure I've got enough. True, true. And then 1, 2, 3, 4, 5, 6. Excellent. Then the next most complex formula is the remainder of the first premise. So P and Q implies R. So let's look at the column for this implication. So we could copy the column for R underneath here. And sometimes that's useful just so that kind of you're comparing truth values very close to each other. For now, I'm just going to kind of check back over. So we have true antecedent, true consequent. This is going to be true. In fact, every line where R is true, again, the entire conditional is true. So that's going to be every other line. 1, 2, 3. There we go. Now, here we've got R being false, but the antecedent being true. So this is a false conditional. Again, here we have P and Q is false. Anytime that P and Q is false, it's the antecedent of the conditional. So again, we know that the conditional is true. So we can just fill in the rest of them. Now, this column, so this implication, is the one that gets combined by a conjunction to this negation. But let's just, rather than trying to like look back at the R column and carry over, a mental negation, let's actually write the negation down here. So this is just going to be false, true, false, true, false, true, false, true. And now we can combine these 2 columns for our conjunction. A conjunction is false if at least one of the conjuncts is false. And here we have true and false, so that's false. Here we have false and true, so false and false. Oh, here's a case where both of them are true. Hurrah! True and false is false, true and true, true, true and false is false, and true is true. So we've got a mixture of trues and falses here. And now we want to look at, let me just grab a new color so that we can keep track of where we're going. We are going to combine this column with just plain old P to figure out what the value of the conjunction is. So the first thing that we can do is we already know that the 4 bottom rows all have to be false because P is false. Then if we look at the top ones, we have that the big complex, the conjunction of the conditional and not R is false here, and false, and false. And now we have one of them where it is true. So this now means that we can combine this conjunction, which is the antecedent, with this column here, which is the consequent, to figure out this final column. We have false implies false, which is true. False implies false, which is true. False implies false, which is true. And false implies false, which is true. Look at that. Every single column underneath the main connective is true. This formula is a tautology, which means that this argument is valid. Every truth value assignment that makes the premises true makes the conclusion true. And that is exactly what we wanted to show. And now I will just close this video by briefly commenting on why we used the notion of validity when we wrote down something like this for a tautology. So using this double turn style. The way that you can think about this is that phi is just the conclusion of an argument that has 0 premises. So we can write down an argument with premises like this, where gamma is just a set of well-formed formulas. So the ones on the left-hand side are the premises, and the ones on the right-hand side, the one on the right-hand side is the conclusion. And then if you just have no premises whatsoever, then you have a tautology. So that's why that notion for a tautology of an individual sentence is intimately related to the notion of validity of an argument. So there you have it. This is what good arguments, how they are defined in propositional logic. I've given you an example and worked through the exhaustive truth table in order to show you that it is in fact valid. Next time, we will move on to some other kind of related notions, questions of implication, semantic equivalence, when two formulas have the same truth value, even if they themselves are not tautologies or contradictions. These are various sorts of semantic notions that are important for understanding just the ways in which truths are related to truths. And I want everybody to have a really good foundation and a grasp in how to use truth tables, what is appropriate to do with them, what are the sorts of interesting questions to ask before we move on to the final part of propositional logic, which is the proof theory. But I'll see you soon. Take care.